So let's get started. So welcome back, everyone. So today we'll be talking about graph embeddings, and this is about how to represent graphs into a kind of like Euclidean space, so you can do analysis on them. So there, and this has become very popular. I asked you last week what you wanted me to talk about in this lecture. So this was the one that seemed the most popular. So we'll talk about this, and we'll get into I'm assuming I don't get too far behind, some kind of practical implications of dealing with embeddings at the end of the lecture as well. So before we get into it, just reminding everyone there's a lot going on at this point in the semester. Your final reports are due at the end of the day today. I pushed back the deadline based on requests from about like 5 to 10 different groups. So I thought that was fair. So the final reports are due at the end of the day today. Make sure as you're finishing those up, look at the project description here and look at what I'm asking for in the final report. Again, 4 pages per person in the group. So 2-person group would be at most 8 pages because I'm going to read everything. Don't cram too much stuff in there. And then make sure these things are clear. Make sure you have a title and your name on it. Problem and motivation, which you probably wrote in your project proposal. What data you explored and how you transformed it. Stuff from the data collection report and your feedback on that. What is the key idea? I want to make it interesting for me. And then explain what you did and how you connected to stuff in class. And it'd be great if you have a conclusion at the end. What you thought. Did this work? Did it not work? You are not penalized for saying you tried these things and you think you followed all the prescriptions, but you don't think it worked as well as you hoped. That sometimes is part of the process, right? So it's okay to report some failures along the way. Okay, so remember to turn those in. Hopefully, most groups are almost or basically done with these projects. The project report. Other thing is the poster outline that will be due next week, Monday. And there's also going to be a kind of a help session on posters on that Monday afternoon. So if you turn in a poster and you're not satisfied with it and you want to get together and share some feedback on this, then that Monday afternoon there will be kind of a help session you could have on that. So as well, and so once you're finished with the reports, then you can make sure you focus on the posters. Again, there will be extra credit for the groups with the most interesting poster as voted on by all of you at the poster session. Okay, and then the actual poster session will be during the exam time, which is a pretty late period in the semester, which is Wednesday, April 30th, from 1 to 3 p.m. We'll have the posters and everything ready there by noon on that day. And if some of you want to go and get stuff set up a bit earlier, that would be great. I will go and start going through stuff a bit earlier as soon as I can, because it's going to take me a while to get through all the posters. Okay, and then don't forget the graphs homework is due on Wednesday next week, but I suggest you do this before the end term test, because you will be asked questions on the interim test that they're not going to be exactly what you do in the homework, but kind of the homework hopefully should prepare you for some of the questions on the graph part of the class on the interim test. Okay, And then that will be here Monday in class. Again, you will get one cheat sheet front and back that you can use on the exam, just like you had before. It will only be from the streaming section up until now, not the earlier part of the class. There might be some stuff that kind of percolated into that. I ordered the class the way I did because you kind of build on some parts of the knowledge. But it will basically be testing on the second half of the class. And I hope its length is about the same length as the midterm test. I hope the scores hopefully I don't have to do any correction on the scores this time. I'm hoping I kind of calibrated a bit better. So that should be in class. Again, I expect the length to be similar to what the midterm test was. And I did post a practice test. Again, I don't specifically plan to post answers for there, but you can ask questions in TA hours or online. Yeah.
Can we expect grades for
homework 6? Did they not get posted already? I expect them to be back soon if they're not already posted. I thought we posted them. Are they posted or not posted? Oh, okay, they're not pushed to Canvas yet. Okay, sorry, we must have forgot the push to Canvas stuff. Thanks for reminding us. Yeah, great. We won't get grades for the graph homework back before the enter. Great. So, any questions on all this? This is our last kind of lecture to ask questions about this. Otherwise, be responsive on Canvas for any questions there. Yeah.
Does the final cover all of it?
Yes. Right. So everything up until today. Yeah, not next Monday's lecture. Yes. Yeah. So it'll be everything up until today. It's great. So let's get into it. So today we're going to talk about graph embeddings. Okay, and what do I mean by this? I mean we often have as our input, so data is going to be a graph, which we'll call G. And we say this is a set of vertices and a set of edges. Again, remember these are the vertices. These are the edges. Right, and so I'm going to draw a graph, and I've been doing these in class, where I'm going to draw a bunch of vertices and then some edges in between these vertices. Okay, so this is a representation of a graph. And we want to do some analysis on these. Often the vertices, we could think of the data, I would say the data, so the data objects are usually the vertices. So think of these are accounts on social media. These are people and their connection to friends in a friends group. They're pages on the internet. Some of the examples we talked about, but the information in the graph, these are usually the edges. Okay, and we're used to, before we got to this point in class, we started talking about graphs where the data points capture the information about the point, right? So it used to be that we have, so before we had, so data x, x1, xn, and we had some distance d, which went from x, that could score some distance or similarity that could score how similar two objects were based on their values, right? So d of x1, x2, where x1 was actually x1, 1, x1, 2, up to x1, say, D. So these were often a subset of our D. And then we did our analysis here. You could take data points, and if you're familiar with kind of machine learning software, if you have data represented as a vector, then you can throw it into kind of your favorite library to do some analysis on it. You can do clustering and whatnot here as well, right? So the idea of the graph embedding is we'd like to take our graph as input and convert it into a representation that we're more so familiar with, where the data objects, which are the vertices, are now embedded as these data points, right? So where these become data points, and then we can just use, like, say, the Euclidean distance. Say what this might be the Euclidean distance between these to do some sort of analysis on it. We can run our clustering, classification, and so on and so on, right? So this is kind of the goal of this this like section, and so how do we do this? Well, it turns out we've actually talked about a number of approaches that basically help us try and solve this problem. So I'm going to kind of go through some of these approaches, and then I'm going to lead up and kind of explain why the approaches we've seen so far in class, which could be applied here and sometimes are usually not the most common approach in graph embedding. There's been a different approach the last almost 10 years or so that has become the most popular thing. So we'll eventually get to that. So the first approach thinks of edges as encoding the similarity in a graph. Right. So if you remember, we have the adjacency matrix of a graph. This was it's an element of 0, 1 to the n by n. We're going to assume that the number of vertices is going to be n, right? So this is a matrix, an n by n matrix with 0, 1, right? And so where we have that aij is going to be equal to 1 if and only if there exists an edge between vi and vj in the edge set of the graph, right? So otherwise, aij is equal to 0, right? So this was the adjacency matrix. And so the first approach we could think about is to say that I'm going to use this as a similarity matrix. S is equal to A. Okay, so I'm going to measure the similarity, and now I'm going to say that the similarity between some VI and VJ, I'm going to encode this as AIJ, right? So basically, I'm measuring the similarity. It's either 0 or 1 versus either similar or not. They're similar if they have an edge. They're not similar if they don't have an edge, right? So what this allows us to do is to then kind of treat this this S as actually let's call it X transpose X for X a matrix in n by d, so into a some d-dimensional space, right? So I'm going to assume S is going to be a positive definite matrix, or I'm going to treat it, I'm going to try to decompose it as best I can by taking, I can do this by the eigendecomposition. I can solve for this, and then I can let xk be the best rank k approximation of x. And so now xk is going to be an element in R n by k. And I could think of that the xk is going to be this matrix now, right? That's going to have k columns and n rows. And if I look at the element xi, which is going to be a row in here, this is going to be an element in Rk. Okay, and so I'm done, actually. This is now the representation corresponding. This point is the embedding of vertex, so VI. Okay, so I've written a bunch of stuff up here. Let's kind of unpack this a little bit. Rank K approximation. Okay, so who can pinpoint? Does anyone recognize what algorithm I've described up here? I've described an algorithm we talked about in class before. I've said the adjacency matrix is going to be, think of it as a similarity matrix. Okay, and then what happened below that is an algorithm we talked about earlier in the semester. Is kind of the second part of an algorithm, basically.
SVD.
Yeah, it's related to the SVD. It's basically this part below here is classical multidimensional scaling, classical MDS. Okay, so basically that started with the distance matrix, and I needed to somehow convert the distance matrix into a similarity matrix. But once I did that, I can just do the eigendecomposition and use that to try and embed it. What the eigendecomposition did, so that I get this from the eigs of S, right? So that gives me an orthogonal matrix, then the eigenvector matrix, and I kind of split that up by taking a square root because it's diagonal and push it into these two pieces, right? So x is actually, x is going to be u to the times lambda to the 1/2, where u lambda is the output of eigendecomposition of S. All right, so I did the eigendecomposition of the matrix S. It's a square matrix. Here I'm going to hope it has positive real eigenvalues. I haven't enforced that as the input, but at least the top one should be defined, and usually the top small number are usually well defined. I get an orthogonal matrix, and I'm going to get a eigenvalue matrix, and I want to turn, and I get the property that U transpose lambda times U gives me recovery of S. That's what the eigendecomposition does. And I'm taking the lambda and splitting it into two parts, lambda to the 1/2 times lambda to the 1/2, and that becomes X transpose. This becomes X, and also, yeah. And so, and that's my representation. I can do a low rank approximation of it by using only the top eigenvalues. Okay, and this gives me the best rank K approximation in terms of capturing kind of the sum of the squared distances in this projection. And if I can just read off of this XK matrix, however many rows I want to read off, this gives me the embedding of each xi. Each xi corresponds with one of the vertices. Okay, so I could just run this, and this would give me A embedding. Yeah.
So just be clear, you're taking the rank K approximation.
Yeah, if I wanted to draw a picture into 2 dimensions, for instance, k was equal to 2, right? If I could use, if it's full rank, I can use the full kind of n-dimensional space. If I want some other d-dimensional space, I can choose that. I don't have a guarantee as positive definite or positive semi-definite necessarily. So maybe not all the eigenvectors and values are meaningful for this, because there might be imaginary and some weird stuff, but usually the top ones are well defined. So usually you don't look at all of them. There's yeah. So okay, so this is a method to take a graph and to draw a picture of a graph. Okay, so we saw this before in class. This is just using the same idea from linear algebra. So okay, so how well do you think this works? It works kind of okay. It's saying that anything that does not have an edge between them, those are not similar at all. So they should be as far away as I can put them. And things that do have an edge between them, I should put them as close together as possible. Right? So this is, so it's, I don't know, it's a pretty kind of crude estimate of the similarity between things. And so it's not capturing a lot of information, but it's a simple thing you can do just out of the box. Okay? Okay, if we were to do, okay, what else? Well, let me mention a couple of other things we could do instead. Let's say I had the adjacency matrix. Adjacency, I can also L1, so normalize this. And then I can go to P. Right, so this way, and L normalize the columns, right? So this is A, and then if I look at the column of A, I'll call this AJ, and I map this to P, where now PJ equals AJ divided by AJ L1 norm, right? So now what I get, all the values were 0, 1, so this becomes a probability vector. That column is now a probability vector, and this becomes the probability transition matrix. Okay, so this is pretty similar to what we did before. Instead of adjacency matrix, now I can do I can say let U lambda U transpose equals P via the eigendecomposition of P, right? And again, now consider the top eigenvector U1. Okay, so if I do this, if I do this and I do the eigendecomposition again, take the top one eigenvector, you know, what this allows me to do is to draw everything on 0. This is U1, and I'm going to get a bunch of V1, V2, you know, V3. I'm going to draw all the vertices on a line now based on their coordinates in this U1 vector, right? So the first coordinate, so V1, this value right here. So this U1 is U1 1, U1 2 up to U1 n. Okay, and so this value U1 1 is the value of V1 on this line. Okay, U1, 2. So the first eigenvector U1, the second value in this coordinate, that's going to be the embedding of the second vertex here. Okay, so what is this telling me if I embed them this way? This is also telling me there's some sort of embedding. I could do this multi-dimensional, but let's just look at the first dimension here. This is the limiting distribution of a Markov chain, right? So if I model the graph as a Markov chain, and let's assume the graph is connected, and then I've done it so I treat it as undirected, because if it's connected, then I can get everywhere, and unless it's cyclic, then it's going to be kind of ergodic, which means that I can think of this as a Markov chain, and this will give me the limiting distribution. Okay, and the points that have a large value after L1, I guess it won't be 0 on here. These will be, I've L1 normalized these, so 0 is here. Okay, but the points that are over here, these have a large probability, right? The sum of these values should be 1, and they all should be between 0 and 1. Okay, so that now it's an embedding, and it's telling me which vertices are likely to be in a kind of, if I do a random walk, which ones am I likely to hit? Okay, so this is also something we saw earlier, just last week. And it gives us some sort of embedding of the graph. But again, this is not a common thing to do. Okay, so, but I could think of this as an embedding into one dimension where the large probability parts of the distribution, these vertices, are off to the right. Okay, so again, I don't know if we're getting any closer, but we're kind of thinking, okay, but maybe this is useful for encoding the graph in one dimension. Okay, the other thing we can do when if I have the adjacency as a similarity S, right, is then to use S as the labeled input to distance, so metric, so learning. Okay, so now I could start with some fairly arbitrary embedding into a high dimensional space using one of the other techniques, but then I can adjust it. So I can basically I want to use S to kind of learn a Mahalanobis distance, or DM, or VI, VJ, or if I start with some embedding, x1, x2, right? Remember, this is x1 minus x2, transpose M x1 minus x2, right? And so now I can actually, if I wanted to use Euclidean distance, or I can write M as A transpose A. I guess I don't want to overuse A here. Let's say as R transpose R, and then kind of multiply, I think, X times R to get back to Euclidean distance. Okay, so instead of doing the scaling inside of here, I think I need to use R inverse here, if I do it correctly. Instead of doing the scaling inside of the distance function, I can basically pre-compute it by multiplying by the inverse, and it will kind of turn it into Euclidean distance. Okay, so again, using the similarity, I can translate this. If I have a base embedding, I can then learn an embedding that tries to respect the similarity. It's a slightly different formulation, but mapping to the distance metric learning problem we talked about. Okay, so again, this is another way to try and get a graph embedding. Again, the adjacency matrix, this has kind of the same shortfall that it's kind of a crude approximation of what's similar and what's not similar. Okay, we're getting a little bit closer, but I want to take a detour to talk about quickly something else we talked about, planar graph. And this is true for small graphs, is a planar graph, okay, VE is a graph that can be drawn in the plane, so that this is equal to, this is R2, with no crossing edges. Okay. Okay, and so if I've got a bunch of vertices, okay, I would like to draw them in such a way so that I don't have any edges which are crossing over each other. Okay, let's say I also have this edge here. Okay, so is this a planar graph? This is actually still a planar graph. It's just not a planar drawing. Okay, I can basically, what can I do? I can flip this one around, so this side is on top, and I can flip this vertex inside of here. Okay, if I redrew it, A, B, let me label them so you see when I redraw it, E, F, G. Now let me try and redraw this carefully. We're going to, A, B, and C, we're going to keep the same. Right, these have, oh, and I have D here. So we're going to have these edges as we did before. But now I'm going to put G over here. And we're going to put, and now we need to draw E and F. I've swapped their order, but they still form this thing with D. And now I can draw between E and B was the last edge I need to draw. And look, I can draw it. Okay, so this is it's the same graph, but in this case, I drew it where no edges are intersecting with each other. Okay, this is the planar graph drawing. Okay, so this would be a planar graph. So drawing. So a planar graph is one where I can draw it with no crossing edges. Yes.
Doesn't reorienting those, like, the locations of those points change any sort of values for, like, edges, or like specifically the values of the vertices?
Well, my input, right, is just the graph, right? The set of vertices and the edges between them. Okay, which vertices have edges between them? That's the same in this and this. Right, so that's all the information. The drawing is the embedding. Okay, so these are two different embeddings of the same graph. This is a planar embedding. This is a non-planar embedding. Okay, and so when I can, I would like a planar embedding, right? If edges are crossing, it's harder to read what's going. So you would prefer a planar embedding in the so in the drawing. Okay. There are algorithms for drawing planar graphs that I think can be done in linear time and the size of the graph. For checking if it is planar, and then if it is planar, for drawing it as a planar graph. You can do both of these. not going to go through those algorithms. But for smaller graphs, you want to draw an embedding, which is planar. That's capturing all the information in the graph. That's kind of the core thing. For much larger graphs, they're less likely to be planar. Okay, so again, I mentioned on the Monday's lecture, the old school version of social network analysis, the graphs were often pretty close to planar. So the questions were really, how can we draw them with no crossings or as few crossings as possible? Or maybe make sure the crossings are not kind of ambiguous in some way or another. Yeah, so this was a challenge. This was kind of an often challenge. And then it's like, okay, how big of a graph and complicated can you draw so that you can still really read all the edges by placing the vertices and then drawing the edges between them. And so it still made sense. I mean, even though this is not planar, you can still see where all the edges are. But if you had, 100 vertices on here and they're kind of overlapping in some sense, it's going to be hard to really pick out what's going on. Or if it's planar, you can still always see it pretty well. Okay, so there's been a lot of work in studying how do you draw planar graphs, how do you when can you guarantee it's planar, and a lot of kind of cool graph theory went into these questions. But they're graphs are so big now that they're often not planar. So this has become less important. One of the methods for how to try and draw stuff at this scale was often these kind of physics and string models, where you try and make the points close together or fix a length of an edge you would like it to be. I would say all edges I would like to be of length 1. Okay, let's say I want this edge to be length 1, this one length 1. I would like them all to be of length 1, and then you kind of put a spring force that if the length deviates from 1, it gets a penalty, and then you allow to move the vertices with used to be called a simulation of the physics. Now you'd call it gradient descent. And so you kind of move the points around until the spring force kind of equalizes. And there's certain knowledge under some types of graphs. If you run a spring minimization algorithm, it will draw them in a planar. But that's not always the case. Okay, so this is another kind of view of graph embedding. In fact, if you look at the Wikipedia page for graph embedding, it's talking about drawing the vertices and the edges so that they make sense together. Okay, but that's kind of not the more modern way it's used. They just want to embed the vertices into a space so I can treat them like data points. And so that's what the previous 3 methods were kind of trying to do. Okay. Any questions on planar graphs? Who had not seen of a planar graph before? Okay, so this is not a new idea. Okay, great. Okay, then the next class of things, is going through the Laplacian, right? And we talked about this before. Now we think about, again, the input. Clear is just the vertex and the edges, but we have the adjacency matrix A, and we have the degree matrix D. Reminder, this is also in R, but it's going to be a diagonal matrix, and DI is going to be equal to the degree of vertex I, and DI not equal to J is going to be equal to 0. All right, so this was the degree matrix, and we talked about 2 versions of the Laplacian: the unnormalized Laplacian L0 was just D minus A, and then what we just called the Laplacian, sometimes called the normalized Laplacian, is going to be equal to the identity matrix minus D to the minus 1 the adjacency matrix d to the negative to the minus 1/2. And this is equal, I can also think of this as d to the minus 1/2 times L0 times d to the minus 1/2. Okay, so these are the unnormalized Laplacian and the Laplacian matrix. Okay, and so similar to when we L1 normalized the adjacency matrix to get the probability transition matrix, and that ensured that just the columns were normalized. This is applying it to both sides of the matrix. So I'm kind of taking the degree distribution, and I'm kind of normalizing the adjacency matrix based on how many edges that each of those vertices have. And I'm splitting the effect onto the left and the right side of the matrix, because we're thinking of it as it's a square matrix, and both the columns and the rows are including basically the same thing. So we need to apply it to both the columns and the rows. But we only want to apply half of it, so we don't apply it twice. Okay, so it's somehow normalizing by the degree effect of the vertices. Okay, and then we learn from, if you remember, spectral clustering. Right, spectral clustering had 2 steps. Step 1 is I wanted to take the top k or the kind of eigen vectors, and again we're going to do L is going to be equal to V lambda V transpose, again through an eigen decomposition. So I'm going to take the top k eigenvectors, Vk, and then step 2, I'm going to partition, let's call this U, because V was vertices, okay? Partition U into clusters. Okay, and so what we talked about in class of how to do this partitioning was that you would just take the top eigenvector, or actually the first eigenvector here was not very meaningful. It basically just encodes the number of it's kind of the uniform matrix. So you start with the top k. It's kind of 2 up through, say, k plus 1. Okay, so the first one is not meaningful here, but otherwise we take the second eigenvector, and then we can partition them into the left and the right, the small and the large, and then we can recursively do this. But another common way of doing it is to project it down to k-dimensional space. Again, maybe this is lambda to the 1/2, and this will be a subset of Rk, okay, into a k-dimensional space. And then here we would run like a k-means clustering algorithm. So there's a lot of very fast kind of clustering algorithms. They do these steps instead of doing this recursively, where you have to do the eigen decomposition over and over again. You do it once, and then once here you run a kind of a like Lloyd's algorithm or some variant with guarantees to find the clusters here. Okay. But what we're advocating in terms of the graph embedding is to just do this. Okay, is just to do this step. Okay, so once I get here, again, I'm reading off of the eigen decomposition, is this U times lambda to the 1/2. This is basically giving me an embedding into this k-dimensional space. Okay, and so this is actually a pretty nice embedding, in that if I think normalized cut that we talked about as a way of defining clusters on these graphs, right? This normalized cut is a good way of thinking about how close data points should be together. Then this will give me an embedding that tries to preserve points close together that would correspond with the normalized cut score. Okay, so this is a reasonable approach to doing kind of a graph embedding based on normalized cuts. Okay, so we'll say this is a nice approach for this normalized cut view of the world. Okay. So kind of normalized cut is kind of a nice measure, I think a pretty reasonable one. But again, there's going to be a slightly more kind of there are other approaches that people feel now model the graph information slightly better than the normalized cut. Let me tell you in just one more slide. Well, before we get there, I want to do another small detour. Is that there's another method I'll mention, Laplacian Eigenmaps. Okay, and so this is approach for manifold. So manifold learning or non-linear dimensionality reduction. Okay, so and the premise here, the premise, and this was very popular around 2005. Okay, is that my data X RD lives on a manifold. Okay, so think of you have some sort of surface. It's like a torus. Yeah, it's my drawing of a torus. And the data kind of lives on the surface of the torus. Okay, and we want to somehow draw it in a Euclidean space so we can measure Euclidean distance. Okay, so now I want to, the idea is I want to map to some space which is Rk. Some k-dimensional Euclidean space. So now these data points, the Euclidean distance here correspond with the distance between the points here. Okay, so the distance is preserved, but I do not draw, I might have points that are far across the manifold. Well, the distance should actually go along the manifold so that these 2 points should be far apart from each other. Okay, so I actually measure this straight. So these 2 points are far apart from each other. They're not close to each other. So if they're far apart on the manifold at geodesic distance, I want them to be far apart here. Okay, and so, okay, so there are a number of approaches that came out around circa 2005. This was kind of, people were extremely excited about this area. This was a prevalent hypothesis. Data lived on a manifold, right? I don't know, data probably doesn't actually live on something as nice as a manifold, but what you would do then is for every data point, you would build this Laplacian Eigenmaps, you would build something like a k-nearest neighbor graph. The k-nearest neighbors for every point vi. Okay, so I'm going to start with data that I assume lives in a manifold, use my nearest neighbor search algorithm to find points nearby. If they're close enough nearby, they're probably also on the manifold. The manifold hypothesis is that locally things look linear, which means I can use the Euclidean distance in a small region. Okay, so I build this graph, and so now I'm going to call this K, right, which is going to be my K nearest neighbor, so graph. And I might do something to make it so it's going to be symmetric. One point's nearest K nearest neighbor, it may not be in the K nearest neighbors of the other points. Okay, so I'll maybe do some tricks to make this so it's symmetric. Not worried about that. And then we just do as before. K is going to be equal to U lambda U transpose by the eigs. And then I will say that my data embedding in RK is going to be my data point Z are just going to be U sub K, where I just take the top eigenvectors of the top K eigenvectors from K, my K nearest neighbor graph. Okay, and so this is Laplacian Eigenmaps. If you want to do manifold learning, this is one approach that you can use. Okay, it has advantages and disadvantages, but it kind of fits in this. Okay, so another way of doing a graph embedding, where you assume the graph is a K nearest neighbor graph that's lying on a manifold. Okay, again, circa 2005. Okay, so around 2015, what happened? What was the big technology around 2015 that influenced how we thought about embeddings? Does anyone remember 2014? Okay. What I'm referring to are these word embeddings that we talked about earlier in the semester, and they were personified by word2vec and glove. Word2vec out of Google and glove out of Stanford. It came out, I think word2vec was out a little bit first, but around 2014, 2015. Okay, and what they did is they took a string of text in large corpus, and it wanted to embed the word text. It would kind of look at the context in the string of text it was found in, and the word text would appear many, many times, right? There'd be another place where you get text, and also in here you get this word text, and you get this words in the context, and there's some neighborhood of the window of the neighboring words in the string of text that somehow gave context to the word text. Okay, and so what I wanted to do was to embed, find v text, so some representation of here, and often they were doing, this was in, let's say, 300 dimensions, seemed to be kind of the right dimension for what we could handle back then. Okay, and with the idea that if two words, let's say the text and the word, if they have that this dot product would be large if the text and word had similar context. So that means their context, the green regions, right? The green regions, this is the context, right? The words in the neighborhood and the strings of text around it. If those were similar, then I would try and embed these into a 300-dimensional space so their dot product was large, right? So the more similar they were, their context, the dot product would be larger. Okay, so this happened around 2015, 2014, 15, and this radically changed how we do natural language processing and led to like ChatGPT eventually. Okay, and so around then, like the next year, there was a kind of a number of groups. First with a paper called DeepWalk. This was out of Stony Brook. And then a couple years later, Node2Vec, this is out of Stanford, said, I want to try and do this for graphs. I want to use this to embed the context, the vertices in the graphs based on their context in the graph. Okay, so I want to do something like this where a vertex is going to kind of appear in these strings. Okay, how do I do this for a graph? Okay, so now I'm going to have my this is DeepWalk. Okay, so I want to think about embedding this vertex, and there are some edges in this graph. Okay, and okay, and these probably go off. Okay, so now I'm going to think of how do we get sequences of something like sequences of words? We were going to replace this with sequences of vertices, and I'm going to do a random walk in the graph. Right, so this would be a random walk in the graph, and this is so for vertex V, these other vertices are in the context window of V if this green line here is a random walk I have in the graph. Okay, and so I'm going to say, well, these are describing the context, and so maybe there's another node here, B prime, where its context is probably going to be similar. The random walks might overlap, so I get some overlap here and here of both of these graphs have the same node in the context. So V and V prime should be embed similar. If on average over a whole bunch of random walks, I think about the limiting distribution of random walks, look at part of the path where V or V prime is in the middle, and look at the distribution of nodes that appear in its context. And I somehow want to capture that as a similarity. And the argument is this should be kind of a richer form of similarity than just using the edges by themselves. And it's a little bit more, it can handle things other than just strong clusters than I could with some normalized cut sort of thing, right? Sometimes normalized cut doesn't know what to do. This one somehow is capturing some nice information. Okay, so I somehow want to capture this in order to do an embedding. Okay, and so this was the rough idea. And now, I mean, so this is around, what was it, 2016 or something, and it's been cited 10, 20,000 times, right? So a lot of people are using this sort of technology, taking big graph data, embed it in Euclidean space, and now kind of do analysis on it. And it seems to work a little bit better than using just the normalized Laplacian. At least that's what these 10,000 papers. Okay. So how can we think about this? What is the similarity actually capturing here? You can try and write, there's some context similarity matrix, context similarity matrix C, right? This is in n by n. Okay, and you can write something down like this. It's roughly, so J in these are, so I'm going to consider walks of, or of my context of length L, right? So remember, this was context is length L, that's the length of the path. And I'm going to consider all steps J, which is within L steps away. Okay, and I need to somehow, there's some degree normalization, and I want to look at the probability transition matrix to the power J. Okay, and I somehow want to scale this. I end up needing to scale this by T divided number of T. So this is there's some scaling factor. So let's see. So this is some scaling factor, not that important. Two here. Okay, what I think is useful to look at is this term. This is the probability transition matrix. Remember, this is the probability transition matrix. Okay, and I'm taking it to the power J. To power J, because I'm assuming now I'm looking something J hops away. Let's say the window's of size 3 and I'm looking at something 2 hops away. Well, I need to think of the probability transition matrix as if I was at V, where could I go in 2 steps? And if I square it, then I'm immediately going 2 steps away. That's what the probability transition matrix squared, because I take 1 step and then I take my next probabilistic step. Okay, and if I want to look 3 steps away, I take it to the 3rd power. And I need to do the DA is some sort of degree scale. Okay, so this is some sort of degree scaling. Don't worry about that either. Okay, so I need to sum over all possible distances away, right? All J and L that I consider within my context, and for each one from V, what's the probability I get that far away? This should be, so I can sum this up together, or I could say so I'm taking the product of all these matrices, and this kind of gives me the limiting distribution inside of a matrix. Okay, so in general, Cij is roughly proportional to the probability that node J is in the context of size L of, or Vj, of node Vi. Okay, so it's the probability node Vj is in the context in here. And so this is kind of what I want to use to guide my embedding. Okay, it's not saying Vi and Vj are similar to each other, but it's saying that, yeah, so it's that they co-occur together. They're in this similar context. Okay, so then I can use this matrix. I could do the eigendecomposition of this matrix. Again, this is not typically what is done in practice. Instead, so this matrix, if the original graph was sparse, so then P would be sparse, but P to the power, let's say 5, is going to become much denser all of a sudden. So I'm really exploding out the amount of information, and then I would have to do eigendecomposition. So instead of doing this, they typically do stochastic gradient descent. So instead of an eigen embedding, do stochastic gradient descent. Okay, and it basically will take a random walk in the graph, use the context of the random graph to be a batch, optimize on the batch, and then take another random walk and kind of optimize. And you need some sort of loss function. So the loss function of the embedding of X. And you kind of embed two matrices. This is the embedding that you care about, and these are the words in context. So it's a little weird. They both embed the vertices themselves and also the vertices to measure the context. Okay, so ultimately you only care about X, okay, but you measure these against each other, and this is often Bj and Y, Cij times log, there's a negative log likelihood of X of the inner product Xi Yj divided by 1 to n of X Xi Yj inner product. Okay, so this form of this like perplexity or whatever, this kind of cost function, you want the dot products X and Y to be large if Cij is. Okay, so basically I want so basically if this is large, then this large. So I want to be maximizing that, but I actually want to minimize a loss function. So I've got a negation in front here. So if the Cij, the context kind of matrix that I'm capturing is large, then I want the inner product to be large as well. Again, this is a common form that you see in these kind of embedding models. Okay. And so you optimize this for the positions of X and Y, which are both in d-dimensional space, and this gives you the embed. Okay, so this is basically how these DeepWalk and node-to-vec algorithms work at a high level. Okay, hopefully put in context of other stuff that we've seen throughout the history. Okay, I want to end on one topic. Okay, I'm calling this warnings about embeddings. And so if I can write especially for language kind of words. Okay, so let's go back to the word embeddings, and this kind of works with any sort of embedding, but the point is that we learn a representation from data. Okay, and if I think about these word embeddings, I can think about that there are these. I'm embedding these words as vectors. So if I embed word v car and v truck, they're probably going to be pretty similar to each other because they're going to have similar context in the sentences they were used. Right. So the idea is car and truck should be embedded in a sort of similar place. Okay, and so when people came up with these embeddings, they realized that this is what they were modeling, that similar context should be similar things, but they also saw things like if I looked for the man and the king, and then I looked at the vector for women, what I can do is I can kind of learn this vector from, this is like a royalty vector. Oh, I drew this, let me, it's a little bit differently here. Just so it'll fit better on the slide. So I'm going to learn a royalty vector. Okay, and now I can apply this royalty vector onto woman. So it's a vector in a 300-dimensional space, right? So I can find this vector, which is this 300-dimensional vector, add it to woman. And what they typically found is that somewhere near here was V queen. Okay, so that if I added the vector onto woman, that royalty vector, then I'd probably get near the vector for queen. This sort of stuff kind of appeared in these embeddings with unintentionally kind of encoding this in there. So this was kind of neat, okay? But if you notice, there's also another vector here. There's this kind of female to male, so gender vector, that's also kind of running through here. You go from women to man, from queen to king, you can kind of see this one as well. Okay. And so this seems like this is useful. In fact, this signal, you can find other words from she to he, from Mrs. to Mr. You could find a lot of these vectors correlated with this female to male gender vector. But what was maybe a kind of unintended side effect, potentially, of this, was that the vector for occupations, let's say V programmer, might be here, and V for secretary might be here, where, okay, they're embedded somewhere in space, that's fine, but if I project them onto the gender vector, it's pretty clear that things like programmer and engineer and lawyer tend to be more on the male end of the spectrum, and secretary and homemaker and stereotypically female professions tend to be on the left side, on the women's side of the spectrum. Okay, and you may say this is stereotypical, but it's also probably statistical, right? And this is a learned embedding from the text they found on the internet. And so this was the context of a secretary, and the language they used was typically female, and the context of the programmer they used typically was male context in some way. And so this is, okay, so this isn't necessarily wrong, but if I built a classifier for someone based on a name, let's say I put a name, John, it will also tend to be a statistically male name will tend to be on the male side. And that may, if I predict, are they going to be a good programmer? Well, that using this somehow in some big machine learning model, it may pick up on this association. Okay, and so this could happen, and we've written some tests that can evaluate, and this can actually happen. Okay, and so this is when you learn these embeddings based on data, you want to kind of think, where is your data coming? What other associations are there in these embeddings? Okay, so we have 5 minutes left, open for comments. What should we do about stuff like this? Could this happen in graph embeddings?
Is there a way that you can select your data better so that you can classify it?
Yeah. Right. So in some settings where they're doing machine learning algorithm, they can say, let's carefully select our training data set to make sure that it's balanced in some way. Right. And this is, there's been some success in this in computer vision with some image data sets. They tried to build representative distributions of faces representing different cultures and different types of people's faces. But most of machine learning now, it's very data hungry, and they train on whatever data they can get. So kind of the core training of these embeddings is typically they want to use as much data as they can, and so they're often not willing to kind of down select from the data that might be more prevalent of one type than. Yeah.
Wondering if maybe there's some sort of hyper. It basically, it'll take this embedding here, and there'll be some probability that it's gonna do the inverse of that. Maybe that would handle for some of those innate biases that might be found in the data.
Yeah. So, okay, so you can try and correct for it at the prediction level. Sometimes the algorithms are okay, so there are kind of two approaches, and you're kind of getting a little bit at both of them. So maybe I'll explain a bit that are actively being looked at. One is to try and identify this gender vector in here and try and remove this from the data. So I could try and say, what is if this is our 300 and this is our 299, what if I projected all the data down orthogonal to this gender vector onto this space here? Okay, and so this kind of removes this correlation because it's been projected out. If I don't want to encode gender information or association in these representations, maybe I can project it out before I pass it downstream. This has some effects, and you can measure some effects. It doesn't completely solve it. Something else they do is they'll run an algorithm, but they'll use these embeddings as the first step, and then they'll train them and fine-tune them. And that fine-tuning will often have a calibration step where they'll pass in some training examples that they want to reach high accuracy on. If it's a female or male name, they want to kind of equalize the probability that they're classified if the other information is the same. And you can pass in some data at a fine-tuning, a later step, that's sort of calibrating the classifier afterwards. So they don't really know how to go in and do kind of surgery inside the classifier. This turns out to be really hard to understand if it's really working or not. So you can either kind of try and modify the representations correctly. This is now called like steering or moving within the representation, or you can try and calibrate with the fine-tuning with your classifier on the backside. And so the second one is kind of less general. You have to do it every time, but this is often done in production for a lot of the tech companies. They're releasing a new product. They run it against these things to make sure that it has somewhat even output. This has sometimes gone wrong at Google so fast now. 6-9 months ago, they released a product with an image generation that was really cool and was so calibrated that they asked questions like, okay, show me a picture of the signing of the Declaration of Independence. And the Declaration of Independence was signed by old white men, and the people in the picture were not old white men. And a lot of people complained about this, that this was not a realistic kind of expectation to be in that picture. So the consensus was that came out after that is that they may have over-calibrated that towards being representative as opposed to being accurate. And so where is the line between these things? I think it's not clear, and it differs from your perspective. And as it is, probably different companies and different products will have different sorts of calibration. And how to deal with this, or how to deal with adjusting the representations on the fly, is something that is active research. All right, but just something to think about when you're doing this, you're kind of can be as implicit associations, and you may or you may not want to have them. So stop here. Okay, and remember to turn your report. Test is on Monday. You'll get a cheat sheet to bring in. All right, thanks. Yep.
So I have a conflict on that day where I won't be able to do it, but I worked out with my group and I'm planning to do like more of making a poster.
Okay.
Like, for this, but I know I'm gonna miss like the writing up the 2 words, and I know it's like take my back.
Yeah.
Okay.
But I was curious if there's a way I could still get partial credit or.
Yeah, you'll get credit for the poster session, the 250 words, if you email TA, the TA Elham, who's been running the poster, the project stuff. She might be able to give you some tasks to do to make up for it. As long as someone from your group is there, I know you, but you also, they have,
Yeah.
Okay. Okay, but I probably won't notice, to be honest. It'll be such a hectic time. So as long as you guys are represented at the poster by your group, we'll be okay. 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 Yeah.
So the gender vector, just the embedding of the word gender, right?
Yeah, it's not necessarily the word gender, but like the words man and woman, or male and female, or his and hers. You can find an association between them.
Okay.
And the technique that like we came up with in our group is you found like the word for man and he and boy and his over here, and then the word for a woman, her, hers, girl over here. And so you could take these vectors and you can find like an average of them, another average here, and look at the vector between the averages.
Okay.
Okay, but there are a number of other proposals out there on how to do this, but this was one we invented for this.
So we can use this vector and we project these other words to this vector and see.
Yeah, so you're just, once you have the vector, you can measure correlation by making a unit vector and taking the dot product. The dot product will just tell you, the larger the dot product, the higher the association. The smaller dot product, the lower the association.
Is there any material to check on this topic?
Yeah. So let me show you. I linked to it. I meant to cover this earlier in the semester, and I just always was running out of time. I linked. I'll move this down on the schedule, but there's a paper. This is an old paper on this topic. Let me find. Maybe I'll post. I want to show you a paper I wrote, which kind of that was kind of one of the first papers on the topic. Something we wrote a paper we called Verb, where we kind of summarized some work we had done, and we built a visualization system that kind of looks at this and figures out what is a good two-dimensional projection that shows these well. How do you find these things? And you could control it and see how it worked.
This is on the campus.
What?
This is on.
I will post it on the link. I haven't, it's not linked now. But here you could choose the words you use to define it, and then you can choose the method you use to, and then you can add in your own words and see how they align. And you can rotate the space without changing the information. So the direction, which we labeled as gender someplace, is the x coordinate, right? And so you start somewhere else, but then you rotate it, so it's x coordinate. So then as far left or right you go, you see how associated. So here, important, strong, practical seems to be more male. Beautiful, gossip tends to be more female, this example. Okay, and then you can project that away to remove that association. That's the result. But there's the paper talks more about this and some literature from when we wrote it in 2021, which is now kind of a long time.
And I don't find references in the textbook onto this topic. So I guess it will not be covered by the exams, right?
Yeah. Anything is possible to be covered by the exam if it was not covered explicitly by the textbook or the lecture notes. I will note that I did last night. I did write up these notes, so these notes are now available on this lecture today. That basically covered everything in the lecture. So I'm not gonna tell you what's is and isn't on the exam. If it's not something that's like a core thing in the textbook, I mean, the textbook was written 4 years ago, and the world's changed a little bit since then. So I can't guarantee things that not in the textbook won't be on, but they probably won't be worth like 20 points, right? Something that if I do ask something, it would be like 2 points or something. One of these more specialized newer topics. Okay.
I have some questions about like how we're